Okay, so in lesson 4.4, we're going to start solving logarithmic and exponential equations. So our first objective says we're going to use like bases to solve exponential equations. And so we saw that the other day when we were solving some stuff. That as long as we could get the bases equal, then we could just kind of ignore our bases and work on our exponents. So that's where we're going to go here. So notice we have on solved problem 1A, it says 5 to the 3x minus 6 is equal to 125. Well, can we take the larger base down to the smaller one? Can we take 125 to a base of 5? And yes, we can. So therefore, let's do that. So 5 to the 3x minus 6 equals 125 is 5 to the third. Now that our bases are equal, we can ignore them and just work with our exponents. So 3x minus 6 equals 3. And let's just algebraically solve that. And so we get x equals 3 as our solution. All right, so try 1A. Pencil problem 1A. So if you want to pause this, you can and try it and then check it. I'm going to go ahead and work it now. All right, so we needed to get like bases, and 64 will go down to a base of 4. Now, what would happen if it wouldn't go down to a base of 4? Then C would 64 and 4 both go down to a base. And they actually will. They'll both go down to a base of 2, but 64 also goes down to a base of 4. So I'm just going to do that. So we're going to keep the one on the left because it's a base of 4 already. And 64 is 4 to the third power. Bases are the same, so ignore them. So 2x minus 1 equals 3. And then we just solve. And we get our solution of x equals 2. All right, so on 1B, well, here's one like I was just talking about. We have base 8 and base 4. So will the 8 go down to a base of 4? It will not. So therefore, then we have to ask ourselves, is there something that 8 and 4 will both go down to a base of? And there is. They'll both go down to a base of 2. So 8 is 2 to the third power to the x plus 2 equals 4 is 2 to the second power to the x minus 3. Now remember, when you have exponents, one base but two exponents like this, you're going to multiply those exponents, which means we're going to distribute the 3 and we're going to distribute the 2. So we get 2 to the 3x plus 6 equals 2 to the 2x minus 6. Bases are the same, so we can ignore those. So we know that 3x plus 6 has to equal 2x minus 6. And let's just solve that. And so we end up with x equals negative 12. Okay, I'm going to solve pencil problem here. So if you want to pause it, go ahead. So again, can 16 go down to a base of 8? It cannot. But 8 and 16 both will go down to a base of 2. So 8 is 2 to the third to the x plus 3 equals 16 is 2 to the fourth to the x minus 1. All right, so again, we got power to a power in our exponent, so we're going to multiply these. So we're going to distribute the 3, and we're going to distribute that 4. So 2 to the 3x plus 9 equals 2 to the 4x minus 4. Bases are the same. So we know that 3x plus 9 has to equal 4x minus 4. All right, let's just algebraically solve this. I'm going to subtract the 3x. I'm going to add the 4. And so we get 13 equals x as our solution. And all of these guys, you can always plug them back in and check, okay? So if you're unsure you did it correct, plug the 13 back in. So in your calculator, you would do 8 raised to the 13 plus 3, which is 16. You'll get an answer, which is approximately 2.8 times 10 to the 14th, I believe. And then you could plug in 16 to the x minus 1, so 13 minus 1, which is 12, and you would get approximately 2.8 times 10 to the 14th. So you know that they are equal then, okay? So you can always check your answers, even if it's not required. All right, so to use logarithms now to solve, let me center this a little better. There we go. All right, now the thing with logarithms, no, never mind, not on this, I'm sorry. It's only when it has a log, what I was about to say. So what if we can't get like bases at all? What if on solved problem 2a here, what if the 8,000 won't go down to a base of 10? Because it won't, okay? In that case, we got to find some way to get that x out of the exponent. And so the only other thing we know to get x out of an exponent is we need to be able to move it over in front of something. But what did we put there to make it move? What did we do to have that, the power property there? So remember, we had to have a logarithm. So as long as what you do to one side of the equation, you do to the other side of the equation, it will keep it equal. So I'm going to take this as a log. I'm going to log both sides. I've got log of 10 to the x equals log of 8,000. Now remember, you could use log or you could use natural log, okay? You know what? Let's actually use natural log. So we'll get the same answer. So we got natural log of 10 to the x equals a natural log of 8,000. All right, so since we have that now, we can take that exponent and move it in front of its log. So we got x natural log of 10 equals a natural log of 8,000. So how could we get rid of that natural log of 10? Well, that's x times natural log of 10, so we're going to divide by it. And so we get x equals, and in our calculator, we're going to have to use that. So we would type in the natural log of 8,000, close that parenthesis, divided by the natural log of 10, close the parenthesis. And it will give us approximately 3.903. Okay, if we want an exact answer, we're going to have to leave it like that, but it won't. All right, let's try pencil problem. All right, same thing. 3.91, or excuse me, 10 will not go down to the base of 3.91. So therefore, I've got to find something that'll help me get that x out of the exponent, and that's a log. So I'm going to take the natural log. Both sides. Oops, sorry. I did not mean to move that x yet. Let me back up. So I'm going to take the natural log of both sides. And if you know you're going to move that x like that, then you can go ahead and do it. But I like to show all my steps. And because we have a log, we can move the exponent in front of it. We're solving for x, so we need to divide by that natural log of 10. And so in our calculators, we're going to type in natural log of 3.91, close the parenthesis, divided by the natural log of 10, close the parenthesis. And we got approximately 0.5922, or 0.592. All right, so 2b, notice the difference is now we don't have that exponential part by itself, do we? So before we can worry about trying to move the x out of the exponent and get like bases, we have to have the exponential piece by itself. So I need to get this e to the 2x by itself first. So it's no different than if we'd have had the problem 7x minus 5 equals 58. How would you get x by itself? Well, you would first tell me you would add 5. So we're going to do that. So 63. And so that's no different than 7x equals 63. So then how would you get that x by itself? You would divide by the 7. And so we get e to the 2x equals 9. Okay? And here we'd have just got x equals 9, but we're not just dealing with an x. Our what was in our x spot, that e to the 2x is what we still have left to deal with. Okay, that was just we're using this to remind us of the steps to solve algebraically. All right, so I can't get like bases. I have a 9 and I have an e, so no way to get like bases. I need to get x out of the exponent. The only way I can do it is to move it in front of a log. So I'm going to log both sides. So I'm going to use the natural log. So the natural log of e to the 2x equals a natural log of 9. Let's move that 2x in front of its log. So 2x natural log of e equals a natural log of 9. Now the nice thing about the natural log of e is we haven't talked about it, but check it out in your calculator. What is the natural log of e? Natural log of e is 1. And we can see that if we work it out algebraically. So if I want to find what the natural log of e is, because remember e is a number, then we can do our base is that little e that's not written. Our x is e, and our y is y. So when we do our b to the y equals x, we would have e to the y equals x. That second e there doesn't have an exponent, so we would have to put a 1 in front of it. So therefore our base is the same, and we see it's just equal to 1. So we have 2x times 1 equals a natural log of 9. Well, 2x times 1 is just 2x. So what it is the natural log of e will cancel, okay? And if there's nothing else there, we have to put the 1. But if we have other stuff there, we don't have to worry with it. All right, then we can divide by the 2 to solve for x. And so x equals, we got the natural log of 9 divided by 2. So in our calculator, we're going to type in the natural log of 9, close the parenthesis, divided by 2. And we get approximately 1.09. I'm sorry, I'm looking at the wrong, 1.099. All right, I'm going to try the practice problem. You can do it. All right, so if you want to pause the video, go ahead and pause the video. All right, so can we get 410 down to a base of 7? Not really sure. So I'm going to go ahead and use our other way of solving so that we can get that x out of the exponent, okay? So I'm going to do my log, and I'm going to do the natural log again. So the natural log of 7 to the x plus 2 equals a natural log of 410. Now, when we go to move the exponent in front of its logarithm, it's that x plus 2 together. So I need to put the x plus 2 together in parentheses, okay? So what I'm going to do now is that x is inside the parenthesis with the x plus 2, so I'm going to get rid of that natural log of 7. So I'm dividing by the natural log of 7. So I end up with x plus 2 equals the natural log of 410 divided by the natural log of 7. And so that I don't mess up and end up with just rounding my answer too early, I'm just going to leave it like that. Still solve for x, so we're going to subtract 2. So we get x equals that natural log of 410 divided by the natural log of 7 minus 2. That would be my exact answer. And so to get our rounded answer, let's type that in our calculator. So the natural log of 410, close your parenthesis, divided by the natural log of 7, close the parenthesis, and then minus 2. And I got 1.092. So what we've done here is on all 4 of these that we did, if we couldn't find the like base, we natural logged both sides. Well, once we got the exponential part by itself, let me stress that. Once we got the exponential part by itself, we logged both sides. We used our power rule, and then we solved for x. All right, so objective 3, it says use exponential form to solve logarithmic equations. All right, now the only difference between what we've been doing and what we're about to do is the fact that before, our x could be anything because we were starting with an exponential equation, okay? We had that base, raised, and exponent in our equation. So remember, the domain of exponentials was negative infinity to infinity, so any x value would work. Now, we have to be careful, though, because when our problem starts with a logarithm, we have to make sure that when we solve for x, when we plug that x back into the equation, that it gives us a number greater than 0, because the domain of a logarithm is greater than 0. So like on this first one here, when I solve, I'll get x equals whatever number. I have to make sure that when I plug it back in and multiply it by 3, it's not negative, okay? Doesn't mean my x can't be a negative number. It means when I plug it back in to whatever we're taking the logs of, it cannot be negative there, okay? And it cannot be 0 either. All right, so the first thing let's do is let's get our logarithm by itself. Just like we just gotten the exponential part by itself, you have to get the log by itself before you can do anything else. So I need to get this by itself, so we can get rid of that 4 by dividing both sides by 4. And so we have the natural log of 3x equals 8 divided by 4 is 2. Now, we're in log form. There's nothing else we can do in log form. But remember, we know that log base b of x is equal to y, and we said if we're trying to solve and we're stuck, we can always change forms. So we can go to b to the y equals x. So that's what we're going to do here. So what is our base? Well, it's a natural log, so remember our base is always going to be an e. So log base b of x is our 3x, equals y, and y is the 2. So when we set it up in exponential form, we have b to the y equals x. And so we're just going to solve for x. And so we'd get x equals e squared divided by 3. Now, oops, I almost forgot to check it. E squared divided by 3 is approximately, so I'm going to go to my calculator. Remember, E is our second ln button. So we could do squared, come out of the exponent or close a parenthesis, depending on which kind of calculator you have, divided by 3. Well, that means it's 2.463 approximately, okay? If I take this number and I'm plug it back in up here, so I'm going to multiply it by 3, is it a number greater than 0? It is. So therefore, this is our answer. And most of the time when there's an e in it, they'll leave it in the form of the e squared divided by 3. But you could definitely, if they told you to round it, you could definitely give it like that. If you're doing it on the test, I like to see it in e form. But if you go this extra step, as long as you have that written, you've got it. So it's no big deal. All right, I'm going to try pencil problem number 3a. All right, so notice on this one, it's got the logarithm by itself, right? It's just log base 4 of the x plus 5. So I've already got the log by itself. I can't do anything else, so I'm going to change forms. So my base is 4, my x is the x plus 5, and my y is 3. So b to the y equals x, and we're just going to solve that. Well, 4 to the third is 64, equals the x plus 5. Subtract the 5, and so we get x equals 59. So let's check it. When I plug it back in, what's 59 plus 5? Well, it's definitely a number greater than 0, right? So therefore, 59 is our answer. Now the other way, if you don't want to have to plug it back in, you can actually think and find what your domain is, okay? So your domain, remember, is whatever you're taking the log of has to be greater than 0. And so if you solve that, your x's have to be greater than negative 5. Is 59? It is. We could have done that on the first one as well, okay? We could have said, well, our domain is our 3x, what we're taking the log of, has to be greater than 0. which means x has to be greater than 0. Is e squared divided by 3 greater than 0? It is, so therefore it was good as well. Okay, so two different ways you can look at it. All right, but look at 3b, solved problem 3b. Okay, it has two logarithms there. Well, we have to have it in log base b of x equals y in order to be able to solve this. Okay, unless I can get a log equals a log, and we're not there yet. So I have log plus log equals a number. So we need to combine these two logs. Remember, we talked about that in 4.3. When they're being added, we can combine them using multiplication. So this is log of x times x minus 3 equals 1. And so I'm just going to simplify that a little bit. So that's log of x squared minus 3x equals 1. Well, now I've got it to a single log. So I have log base b of x equals y. So our base is 10, because there's not 1 written, and it says log. Our x is x squared minus 3x, and our y is 1. So when I set this up into exponential form, we have b to the y equals x. Remember, anytime you have an x squared and an x, you're going to need to factor. In order to factor, you're going to have to set this equal to 0. So that 10 to the first is just 10. And so we're going to set this equal to 0, so I'm going to move the 10 over. So 0 equals x squared minus 3x minus 10. Now, since it is quadratic, I said factor, but you could also use your quadratic formula if you wanted to, okay? But this one is factorable, so I'm going to go ahead and do that. So we're going to factor this. We know our first terms have to give us x squared, so it's going to be x and x. We know the last two numbers have to multiply to 10, and they're going to need to subtract to 3. So that's what, 5 and 2, and I need a negative 5 and a positive 2 to give me that negative 3. And this is still equal to 0. So therefore I can set both of my equations, or both of my factors, equal to 0 and solve. So we get negative 2, and we get 5. But remember, because we had a logarithm at the beginning, we got to plug them back in and make sure that it will work on both of them, okay? So I'm changing colors here. So my first one is x. If I plug in 5, that's fine. If I plug in negative 2, that doesn't work, right? We can't take log of a negative 2. So therefore 5 worked. But I still have to check the other one, okay? My other was log of x minus 3. Well, when I plug in this 5 here, that's 5 minus 3, which is 2. 2 is positive. That works. So there is our only solution. Okay, we could have also, remember, looked at it from the domain perspective. The first one was an x, so we know x has to be greater than 0 for it. And the second one was x minus 3. So that's got to be greater than 0, but when we solve it, that says x has got to be greater than 3. So the negative 2 one lost out on both of them, but the 5 is true for both. It has to work on every single log, okay? All right, pencil problem. Same idea. We've got two different logs there, so we need to combine them. They're being added, so I'm going to combine them using multiplication. So log base 5 of x times 4x minus 1 equals 1. So I'm just going to kind of clean that up a little bit now. Something I just thought about that I should have pointed out too is when we have logs, we can only combine them if they're logs of the same base, okay? So all the ones that we're probably going to encounter will be logs of the same base, but double check that just in case. All right, so I'm going to just clean this up by multiplying that. Now we've got our single log. So therefore we can change to exponential. So our base is 5. Our x is a 4x squared minus x. And our y is 1. So we do b to the y equals our x. Because we have x squared and x, we know we need to set equal to 0. So we can factor or use quadratic formula. So 5 to the first is 5. So we'll move the 5 over. So we got 0 equals 4x squared minus x minus 5. All right, so to factor this, it's still a trinomial, but this is the one that y'all learned where it's like first times the last, or I call it the alien. So we're going to multiply by the 4. Remember, you multiply the last number by the first number. So that gives us x squared minus x minus 20. Then we just factor this like we did the last one. So x and x to give me the x squared. Two numbers that multiply to 20 that will subtract to a 1, so 5 and 4. I need a negative 1, so negative 5 and positive 4. But remember, before we were done here, but we multiplied at the beginning, so we got to divide that 4 that we multiplied by back out. And so this gives us 4x minus 5 times x plus 1. And this is still equal to 0. So set them each equal to 0 and solve. So we got 5/4 and 1 is our answer. So we need to check and see this x here. I'm going to do it using domain. I kind of like that idea. I don't know why I didn't do it first. So the domain, we know the x has to be greater than 0. Is 5/4 greater than 0? It is. What about negative 1? It is not. So it's automatically not an answer for this problem. And then we know that 4x minus 1 has to be greater than 0, which means 4x has to be greater than 1, divided by the 4, so x is greater than 1/4. Is 5/4 greater than 1/4? It is. So therefore, 5/4 would be our answer. These are important, guys. You can't forget to check the domain. If you forget to check to see does it work, you're going to miss a lot of them because they tend to put those in there to make sure you're checking it. All right, so let's keep going then. All right, so it says use the one-to-one property of logarithms to solve logarithmic equations. So remember when we were doing the exponents earlier, and we had like 5 to the x equals 5 to the third, and we said, well, our bases are the same, so we could get rid of them and just say x equals 3. Well, it's the same thing if I had log of x equals log of 7. As long as my log bases are the same, I can get rid of them, and then that means that x has to equal 7. So we're going to do the same exact thing here when we have a whole lot of logarithms. All right, so notice on solve problem number 4, we have 3 different logarithms. 2 of them are on the same side, so I could combine them. So we got our natural log of x minus 3 equals. Now when I combine these, they're being subtracted, which means we combine them using division. So we're going to write the natural log once, and we'll put the first one on top, divided by the bottom one. Now we could still move the other logarithm over if you want, and then you got fractions within fractions, and you get to deal with all of that fun stuff. But the easiest way, as long as you just have a log equals a log, and they have the same base, is that one-to-one property that says then I can ignore the fact that they're logarithms, and I can set x minus 3 equal to 7x minus 23 over x plus 1. And it does get a little messy on this one. Boy, they picked a good one for us to have to deal with here at first. All right, so, but remember, either you want to get rid of the fraction, or because you have a fraction and with an equal sign here, we could put that over 1 and just cross multiply. So we end up with x plus 1 times x minus 3 equals 1 times 7x minus 23. All right, I'm going to have to do FOIL over here. So x squared minus 3x plus x minus 3, which gives me x squared minus 2x minus 3. Okay, over here I'm just going to distribute the 1, so I just get 7x minus, can't read my own handwriting, 23. Sorry. All right, we also have x squared and x, so that means that we need to get this set equal to 0 so we can factor. X squared is positive where it's at, so I'm not going to touch that side, so I'm going to move the 7x over. And I'm going to move the negative 23 over. I should have wrote smaller. So we get x squared minus 9x plus 20 equals 0. All right, so I'm going to come over here, and write that. So we had x squared minus 9x plus 20 equals 0. And so I'm going to factor this. So x and x. Two numbers that multiply to 20 that add to 9, 5 and 4. I need a negative 9, so they're both going to be negative. All right, set them each equal to 0 and solve. So add the 5, add the 4. But remember, you have to check your answers still. So this one says that x minus 3 has to be greater than 0, which means x has to be greater than 3. Are they both greater than 3? Yep, so they're good for the first one. Okay, the second one says that 7x minus 23 has to be greater than 0. I'm going to go write this on the side. So 7x minus 23 is greater than 0. Move the 23 over, so 7x is greater than 23, and then divide by 7. So x is greater than, and so I can get a decimal approximation. I'll put it in my calculator. Let me make sure my calculator is clear before I put it in. And it's like 3.3. Okay, since ours are whole numbers, I just looked at that. Are they both greater than 3.3? They are. And then the x plus 1 has to be greater than 0, which that was pretty easy. Subtract the 1, so x is greater than negative 1. Are they all greater than negative 1? They are. So that means both of these are our solutions. All right, pencil problem number 4. Same idea here. We've got 3 different logarithms. These two are on the same side. Now, if it had like a plus 4 on this side as well, then that means we're going to have to do our log base b of x equals y. It means we'd have to get all the logs on one side, okay? But this is just nothing but logarithms, so we can combine so that we can get a log equals a log. So they're being subtracted, so we're going to combine them through division. So log of x plus 4 over 2 equals log of 5x plus 1. All right, we got log equals a log, so we can cancel them. So we know that x plus 4 over 2 is equal to 5x plus 1 over 1. Cross multiply and divide. So 2 times 5x plus 1 equals 1 times x plus 4. Distribute. Distribute. And solve for x. So divide by 9, and we get x is equal to 2 over 9. Now remember, you have to check your domains, okay? So for this first one, x plus 4 has to be greater than 0, which means x has to be greater than negative 4. Is 2/9 greater than negative 4? It is. Okay, this is just log of 2. There's no x to plug in, so you don't have to worry about it, okay? And then we have the 5x plus 1 has to be greater than 0. I'm going to come work that over here because it's got a couple steps. So that means subtract the 1, so 5x is greater than negative 1. Divide by the 5, so x is greater than negative 1/5. Is 2/9 greater than negative 1/5? Yes, because 2/9 is positive and the 1/5 was negative. So it's definitely greater than it. So it worked on all of our logarithms, so therefore there is our solution. Just have to make sure it's within the domain. All right, and the last part, application. All right, so solve problem 5. Says medical research indicates that the risk of having a car accident increases exponentially as the concentration of alcohol in the blood increases. The risk is modeled by R is equal to 6e raised to the 12.77x, where X is the blood alcohol concentration and R is given as a percent, is the risk of having a car accident. Oh, I'm sorry. And R, given as a percent, is the risk of having a car accident. What blood alcohol level concentration corresponds to a 7% risk of a car accident? All right. So they gave us our equation here. Remember, make sure you understand what the variables are, okay? What is X? X is the blood alcohol concentration, and R is the risk of having an accident as a percent, okay? So the question it says is what blood alcohol concentration, so that means we're after X, corresponds to 7% risk of a car accident. That's our R. And remember, R is given as a percent, so we're going to use the 7. We're not going to change it to a decimal. So we have 7 equals 6e to the 12.77x. We just got to solve for x. So first thing is my exponential, the exponent and the base are not by themselves, so I need to get them there. So we're going to divide by the 6. And that's an ugly decimal, so I'm just going to leave it as 7 over 6 equals e to the 12.77x. Now, I can't get like bases, so remember, if we can't get like bases, we're going to log both sides. So we're going to have the natural log of 7/6 equals a natural log of e to the 12.77x. Well, we did that so that we could get that x out of the exponent, so we're going to take the entire exponent and put it in front of its logarithm. So I'm going to go up here. So we end up with the natural log of 7 over 6 equals 12.77x natural log of e. Do you remember what we said natural log of e is? It is 1, and anything times 1 is itself. So we can just get rid of that. So we know the natural log of 7/6 is equal to 12.77x. So to solve for x, we're going to divide by the 12.77. And so we get x equals, so we're going to plug this in our calculator, so the natural log of 7 divided by 6, close your parenthesis, divided by 12.77. And I got 0.012. Now, this started out as an exponential equation, so I don't have to worry about is the domain, because remember, domain of exponentials is negative infinity to infinity. All right, pencil problem. It says the formula A equals 37.3 e to the 0.0095 e models the population of California, A in millions, T years after 2010. When did the population of California reach 40 million? All right, so they gave us an equation. So let's make sure we understand what those variables are. This E actually is supposed to be a T. It's a typo. It doesn't have a T in the problem. All right, so what is A? It's a population of California in millions. What is T? The years after 2010. So it wants to know when, so we're looking for T, did the population of California reach 40 million? So this 40 million is our A. And we're after T. All right, so we're going to plug in. Remember, A was in millions, so just plug in 40. Okay, my T is in that exponent, so I got to get the exponential part by itself, so the base and the exponent. So I need to get rid of the 37.3. So let's divide by 37.3. And for right now, just so I don't have a bunch of decimals, we don't like to round into the very end, so I'm just going to leave that as a fraction. It's not my answer, so it's okay if I got a decimal in that fraction, okay? So we got 40 over 37.3 equals E, that's a funky E, E to the 0.0095t. We need to get that t out of the exponent, so we're going to natural log both sides. Remember, we do that so we can get that exponent piece in front of it. So we got the natural log of 40 over 37.3 equals 0.0095t times the natural log of e. Natural log of e is 1, so times the other stuff, it would just be the other stuff. We're going to divide by the 0.0095 to solve for t. All right, so we'll get t equals, in our calculators, we're going to type in the natural log. Oops, 1 second. Okay, so we're ready to type this in our calculator. So we're going to type in the natural log of 40 divided by 37.3, close your parenthesis, divided by 0.0095. And I got 7.356. And so let's see, t is in years, so that would be years. So it did say when did the population, so it's in 7.356 years, but remember it also says that t years after 2010, so this would be after 2010, or we could say what year is that? Well, 2010 plus the 7.356 is sometime in the middle of the year 2017. All right. So 5B, solve problem, says how long to the nearest tenth of a year will it take $1,000 to grow to $3,600 at an annual rate of 8% compounded quarterly? So these are those formulas we looked at when we were doing the exponentials. And because remember we had the compounded everything except continuously. We had a equals p times 1 plus r over n raised to the nt. And then we had, if it was compounded continuously, that was a equals pe raised to the rt. All right, this one says compounded quarterly, so it's going to be the first equation there. So it says how long, so we're looking for t, to the nearest tenth of a year will it take $1,000 to grow? So, well, let me just go ahead and put my variables out here. All right, and it said how long, so we know t is what we're after. The 1,000 is the amount that's going to start with, so that's our p. It wants to grow to 3,600, so that's what we want for our ending amount to be. At an annual rate of 8%, but remember, you have to write that as a decimal, so 0.08, 2 places to the left. Compounded quarterly. Quarterly means there are 4 times a year. All right, so we're going to plug it into our equation. So we have, I'm going to write out the equation here. So a equals p times 1 plus r over n raised to the nt. So our a is 3,600. Our p is 1,000 times 1 plus r, 0.08, divided by 4 raised to the 4 times t. All right, so let's see what we can simplify here. We know we've got to get the exponential part and the base by itself, okay? So let's go ahead and simplify what's inside that parentheses, but I also know I'm going to have to get rid of that 1,000. So let's divide by 1,000. So 3.6 equals 1 plus 0.08 divided by 4. 1 plus 0.08 divided by 4 is 1.02 raised to the 4t. Now, can we get like bases? We don't have a clue, right? But we know that if we can't get like bases, or even if we can still take the logarithm of both sides. So I'm going to take the natural log of 3.6, and that's equal to the natural log of 1.02 raised to the 4t. Then we can move that exponent in front of its log. So the natural log of 3.6 equals 4t natural log of 1.02. Now I want to get t by itself, and everything's being multiplied here. So I can divide by 4 times the natural log of 1.02. That'll get rid of both of those. So divide by 4 times the natural log of 1.02. Now, when we go to type this in our calculator, okay, we have to tell it that entire bottom's together. Otherwise, it's going to read it as a natural log of 3.6 divided by 4, and then get an answer and multiply that times that log of 1.02. So when we go to put this in our calculator, remember when you open a log, you got to close it. But then also when we do that, let me go ahead and do that for this one. But we also have to tell it, hey, this whole thing is on bottom together. So you have to put a parenthesis on the outside there. So I'm going to type it in, the natural log of 3.6 divided by open parenthesis. Hold on, let me start over again. I'm sorry. The natural log, it opens it, 3.6, close your parenthesis, divided by open parenthesis, 4 natural log, it opened a parenthesis, so 1.02, close that natural log, close the bottom, and hit enter. And so when we did this, I got 16.171. And we want to know to the nearest tenth of a year, so tenth is 1 decimal place, so we would say 16.2 years. All right, and what you've been waiting for all lesson, pencil problem 5B. How long to the nearest tenth of a year will it take 35,000 to grow to 70,000 at 8% interest compounded continuously? So remember, compounded continuously is the PERT formula. So A equals PE raised to the RT. All right, so A, P, remember E is a number, so it's not a variable, R and T. Now, this is how long to the nearest tenth, so we're after time, will it take 35,000 to grow, so 35,000 is what we're going to start with, to grow to 70,000, so that's our ending amount, at 8% annual interest. So our rate is 8%, but remember, change that to a decimal. All right, so let's plug it into our equation. So 70,000 equals 35,000 e to the 0.08 t. Well, again, we got to get that base and exponent by itself, so let's divide by the 35,000. So we get 2 equals e to the 0.08 t. All right, so we're stuck in exponential form, so let's go to log form. So the natural log of 2 equals the natural log of e to the 0.08 t. Now we can move that exponent in front of its log. Natural log of 2 equals 0.08 t, natural log of e. Remember, natural log of e is 1, so 1 times 0.08 t is just 0.08 t. Divide by the 0.08. And so we get t equals, so my calculator, natural log of 2, close my parenthesis, divided by 0.08. And I get 8.664, but it says to the nearest tenth. How long to the nearest tenth? So that would be 8.7 years. All right, guys, and that is the end of section 4.4.